So in this video, we are going to discuss alcohols and thiols. Thiols are basically just sulfur analogs of alcohols, so the majority of this video will focus on alcohols. The first thing we want to discuss is how we classify them. Just like with a carbon, we have a classification system for alcohols. So you can have a primary alcohol. And remembering from when we learned our functional groups, an alcohol is simply just, say, R for rest of molecule. We'll throw in a primary carbon, which is attached to a hydroxyl group. So here we have a primary carbon. So therefore here we have a primary alcohol. And the same thing goes for secondary and tertiary alcohols, right? We have a secondary carbon, so we have R, another R, CH, and then the hydroxyl group, which makes it an alcohol. And for a tertiary alcohol, we would have three R groups, R, and then C, R, R. This would be reminiscent of the substitution elimination chapter. So as a review, we have here a secondary carbon. So we have a secondary alcohol. Here we have a tertiary carbon. And so we have a tertiary alcohol. The chemistry of these species is going to be different depending on the type of alcohol that you have. So before we get into that, let's talk a little bit about how we name them. So for the nomenclature, we have common nomenclature system, and we have IUPAC, or the systematic nomenclature system. So with common nomenclature, you're going to name the alkyl group to which the hydroxyl group is attached, and then you're just going to follow it up with the word alcohol. With the IUPAC system, we're going to use a suffix OL, like all, right, to denote the hydroxyl group. So you're basically just going to take the alkane or the parent alkane name, and you're going to replace the E on the end of it with an OL. So for example, I could have something like that. And with IUPAC, so I'll just put these over here. And then we'll do common underneath. With IUPAC nomenclature, we are basically going to say, hey, what was that alkane before we put the OH on the end of it? And it was ethane, right? We're going to replace the E of the ethane with OL, and we're going to call it ethanol. For common nomenclature, we're going to say, hey, what's the alkyl group attached to the hydroxyl group? It's an ethyl group. So we have ethyl. And then we're just going to slap on the word alcohol. So let's do one more. We could take like this right here. So notice how in that first example, we had a primary alcohol. In the second example, we have a secondary alcohol, right? All depends on the carbon to which the hydroxyl group is attached. With IUPAC nomenclature for that particular species there on the right, we have to say to somebody, hey, look, this is not just propanol, right? Because it's a derivative of propane, but the hydroxyl group is on the second carbon, not the first carbon. So you have to let someone know that. So we've got 2 dash, instead of propane, we have propanol. In common nomenclature, we're going to take the name of the alkyl group that's attached to the hydroxyl group, and then we're just going to follow it up with the word alcohol. So that group, that alkyl group that's attached to the hydroxyl group, is an isopropyl group. And then we'll just say alcohol. Sometimes we'll smush the two together. I'm sure you've heard of isopropanol, right? So oftentimes we'll take common names for alkyl groups and we'll use them in IUPAC nomenclature. And often we do that for super common molecules, or sometimes you'll see it done where it's easier to give the common name for the alkyl group and use it in systematic nomenclature because there are other substituents on the molecule, and it's more convenient to have a number for which to identify them, what carbon they're on, right? So sometimes it's just a little bit easier to put the two different systems together. Let's just do a few examples of molecules that may have substituents um, located on the molecule. So if there's a functional group suffix, in other words, you've got an alcohol, right? So we have an OL suffix, and there's also a substituent. The functional group suffix is going to take priority, like usual, right? So we're going to give priority to the functional group. In other words, it's going to get the lowest number. So for something like this, and we'll just put like a bromo group on the end. We're going to count the carbons. You're going to find your longest continuous chain of carbons like you normally would if you were naming an alkane, but you want to make sure that you give the lowest possible number to the hydroxyl group. So in this instance, then we're going to count in this direction. 1, 2, 3. And so we're going to name this thing 3-bromo. And remember to put a hyphen between the 3 and the bromo. Dash 1 dash propanol. Let's do one more. So we could have something like this. So we're going to find our longest continuous chain of carbons that gives the lowest number to our functional group. The functional group that we have here is the hydroxyl group, right? So we have the alcohol, and coming from this direction gives it the lowest possible number. The longest continuous chain of carbons is going to be 5. So this is like a pentane derivative. We notice that on carbon 4, we have 2 methyl groups, right? So we have 2 substituents hanging out on the 4th carbon. We also have to concern ourselves with the hydroxyl group. So in this instance, we're going to call this 4,4 dash dimethyl dash 2. And because this is a derivative of pentane, we're going to drop the E and put OL, so pentanol. So again, just like all other nomenclature, we're going to be giving priority to the functional group. And when we say we're giving priority to the functional group, it means that we're going to be giving it the lowest possible number. Let's do a ring just to get some practice with those. So for example, we can keep it simple and just keep stereochemistry out of it. You have a ring, you have to be careful because your functional group is going to be taking priority, meaning it's going to be the lowest possible numbered carbon. So on the ring, you have the option to count in 2 different directions. You want to count in the direction that gives your other substituents the lowest possible number after you prioritize the functional group. So this will be carbon 1, this will be carbon 2, and that would be carbon 3, instead of going the other way around the ring where that would put the methyl group on carbon 5. So after you've prioritized the hydroxyl group, you want to make sure then that your other substituents are going to get the lowest possible number. So this becomes therefore 3-methyl. And instead of cyclohexane, it'll be cyclohexanol. You only use hyphens to separate numbers from letters, or there's an exception with amines and amides when we're indicating that a group is actually on the nitrogen. So if you're going to be separating something that indicates position from the actual name of the substituent, then you'll put a hyphen in. But we're not going to put a hyphen between methyl and cyclohexanol, okay? So it's 3-methyl cyclohexanol. Let's see. If you have more than one substituent, then your substituents are going to be named in alphabetical order. And so that's kind of like the same thing we've been doing with our alkanes, right? So you could have something like this. I guess we could just put methylene and stick the hydroxyl group here. So again, you want to count this thing in a direction that gives priority to the alcohol. So we're going to come at this from the right. So we've got 1, 2, 3, 4. Now I could go up into that ethyl group and go 5, 6, or I could keep going to the left because I got an extra carbon. That's my longest continuous chain. So 5, 6, 7, right? So that would have been heptane, but it is now heptanol. And so therefore we're going to be giving the bromo group to carbon 6, and the ethyl group is hanging out on carbon 4. These are going to be placed in alphabetical order. So here's where I've seen people get confused, where they want to give, just because bromo comes first in the alphabet, they want to try to give the lower number to that. No, you're giving the lower number, you're giving priority to the functional group, and then wherever the other groups end up, whatever carbons they're on, that's their number. But in the name, you're going to alphabetize your substituents. So this will be a 6-bromo -4-ethyl Now, you know you have a heptanol, but you have to let someone know that the hydroxyl group is hanging out on carbon 2. So you'll put a 2 dash heptanol. So these are named pretty much just like the alkanes, right? So when we were in that chapter, we spent a little extra time on that nomenclature because we were like, hey, you know what? We're going to be using this technique for all the other functional groups. You're going to find your longest continuous chain and you're going to prioritize the functional group. Your substituents are going to be put on whatever carbon number they land on, and we are going to alphabetize them. If you end up getting the same number in either direction, then you want to go for the lowest possible number for your substituents, of course. But you're going to be prioritizing your functional group first and foremost. So let's talk a little bit about the physical properties of alcohols and their reactions. So alcohols are weak acids, right? pKa is pretty close to that of water, so somewhere around 15 or 16, right? What that means for us is that the conjugate base is going to be pretty strong. So using just methanol to keep it simple, if we were going to do some chemistry on this molecule, like say we wanted to do a substitution reaction and say you wanted to attack that carbon with some nucleophile, then the leaving group would have been the hydroxide anion, right? So this right here would have been a strongly basic leaving group, which means that as it is, the alcohol, if it's going to undergo a substitution reaction, we're going to have to do something to that hydroxyl group to make it a better leaving group. Because if we wanted to do this reaction, for example, say you want to attack it with that, and you wanted to do this, make the alkyl halide, that's not happening. The hydroxide anion is too strong of a base, so it is too poor of a leaving group. But here's the deal. If you convert that hydroxyl group into a weaker base somehow, like say you wanted to have that reaction occur and you decided maybe if I protonate the hydroxyl group, then the leaving group is water, right? You can change this around and actually make that alkyl halide, just changing the reaction conditions. So instead of bromide, what if I let this react with hydrobromic acid? So here you have a poor leaving group. It's too basic. But if I protonate it using hydrobromic acid, what I get is a better leaving group because I get a weaker base. This is still floating around in the pot. So this right here is a good leaving group, right? It's a weaker base. So this comes in, and of course, using its electrons, I'm going to attack that carbon. Water is going to take off, usually with a little encouragement in the form of heat, and we end up with methyl bromide. And your leaving group is water. So this right here is a weaker base than hydroxide. Remember, the weaker the base, the better the leaving group. So with alcohols, we can do all the same chemistry pretty much that we could do with an alkyl halide. We just have to tweak the reaction conditions a little bit, right? We have to understand what the leaving group is going to be, depending on what we're going to be doing. And we have to sort of, set up our method accordingly. So since the hydroxyl group of the alcohol has to be protonated before we can displace it with the nucleophile, really only weakly basic nucleophiles can be used in a substitution reaction. So if you have a moderately strong or a strongly basic nucleophile, you're not going to be able to use this as a nucleophile in a substitution reaction with an alcohol, because then they would become protonated in the acidic solution, wouldn't they? And once they become protonated, they're no longer nucleophiles, right? Or they would be really crappy nucleophiles. So you have to do these sort of substitution reactions under these acidic conditions with the alcohol, because we have to protonate the hydroxyl group. But if you want to use a really strong nucleophile, you're going to end up protonating that basic nucleophile, aren't you? If under acidic conditions, and then you no longer have a strong nucleophile. You also may no longer have some acid, so you're not going to be protonating the alcohol, and therefore you're not going to create the good leaving group in the form of water in order to encourage the substitution reaction. So something to keep in mind, we need to protonate the hydroxyl group of the alcohol, encourage it to take off, right? Create a good leaving group in the form of water, and then use a weak nucleophile, weakly basic or neutral nucleophile, right? Iodide, bromide, chloride, something like that. So something else to keep in mind, primary, secondary, and tertiary alcohols are all able to undergo nucleophilic substitution reactions with, say, hydroiodic acid, hydrobromic acid, hydrochloric acid to form alkyl halides, like in the reaction that we just looked at. But only the tertiary alcohol is going to need to be heated. So here I had given a primary alcohol and said, hey, let's give it a little encouragement in the form of heat, right? Really sort of, I guess, in reality, only the tertiary alcohol really needs to be heated. But we can write down sort of an example for each. So we could take a primary alcohol. It's also worth noting the type of mechanism or the mechanistic pathway believe these to undergo. So here we have a primary alcohol, right? We can allow this to react with a really strong acid, HI, and we end up with the alkyl halide. So thinking ahead about what type of chemistry or what type of nucleophilic substitution reaction we can do with a primary alcohol, once you've protonated the hydroxyl group, you've created a good leaving group, and the nucleophile can come in and do a backside attack on that unhindered carbon. So this right here would be an SN2 process. We could take a secondary alcohol and we could allow this to react with a strong acid, say HBr. We'll get the alkyl halide. And some water. So again, thinking about what happens here, we've got a situation where we're going to protonate the hydroxyl group, and we are going to create a good leaving group. We're going to come in and attack the carbon that bears the leaving group. It is unlikely that a secondary or a tertiary, so draw one of those in there, alcohol is going to undergo an SN2 reaction. It is more likely to undergo an SN1. So you can draw this in, creating the alkyl halide. So if you were asked about the mechanistic pathway here, it's more likely that these more hindered carbons will proceed through an SN1 pathway. Remember, with SN2, the primary alkyl halides and primary alcohols, and as we'll see, primary amines, can undergo SN2 processes. We have a relatively unhindered carbon. We're not creating that carbocation in the SN2 process, right? Because that primary carbocation would be too unstable. But a secondary or a tertiary would be more stabilized, right? And so it's probably the SN1 pathway where these particular alcohols are going to react. Under nucleophilic substitution reaction, you can create a secondary or a tertiary carbocation like we saw in the substitution elimination chapter. So you'll be protonating the alcohol in all cases, right? You'll be using the acidic hydrogen in each of these molecules to protonate your hydroxyl group. And you'll create an equivalent of water that will be your leaving group. And you'll end up with your alkyl halide. There's another type of reaction we can do with an alcohol, and it's an elimination type of reaction. So let's label these. These are going to be our substitution reactions. Nucleophilic substitution. We can also do eliminations. So, probably need some heat for that one. With the elimination reactions, we have a name for this type of reaction with alcohols. It's called a dehydration reaction. And it's going to be acid catalyzed. So again, we're going to have to protonate the hydroxyl group and create a good leaving group. So again, in the form of water, right? So the alcohol can undergo an elimination reaction by losing the hydroxyl group and a proton from an adjacent carbon. So for example, I could take cyclohexanol and I could cook this up with some sulfuric acid. So that little triangle means heat. And what you're going to lose is, and I'll draw this in, you're going to lose the hydroxyl group, this, and this. So we're going to protonate the hydroxyl group with the acid, and we're going to lose water, and we're going to lose that proton. And the product that you get is going to be an alkene. Plus water, so that's your leaving group, and it's catalytic in acid, right? So after we protonate the hydroxyl group in order to create the better leaving group, then the conjugate base of our acid is going to come in and take away that hydrogen. So let me show you sort of how this works. We could draw in our lone pairs so we could see what's going on. So here, and I'll just draw H plus instead of H2SO4, right? It is a source of H plus after it protonates the water. So really it could be H plus, H3O plus, or you could draw H2SO4. But we're essentially going to be protonating the hydroxyl group to create a good leaving group. And then this is going to take off. So water is going to depart or leave, right? And you're going to form that secondary carbocation. And again, the rate at which this occurs depends on the stability of the carbocation. So you have your carbocation, and then I'm going to draw this little hydrogen in here. Either water comes in or the conjugate base of your acid catalyst. Some kind of a source of electrons will come in and take that hydrogen away, and these electrons will come down and quench that positive charge. And what you get is your alkene. You'll also get your acid catalyst back again. So this would be the dehydration of a secondary alcohol. In this particular case, because we're forming the carbocation, and then we're coming in and taking the proton from the beta carbon. Remember this? This is an E1 process. So dehydration reactions for secondary and tertiary alcohols follow an E1 mechanism. So again, to recap, the acid is going to protonate the most basic atom in the reactant, and in this case, it's the hydroxyl group. Water is going to leave, leaving behind a carbocation, and then the base in the reaction mixture, so in this case, water or whatever is most basic and present in the highest concentration, right? So water is probably going to be the base that removes the proton. It will take a proton off of the beta carbon, that is the carbon adjacent to the positively charged carbon, your carbocation, and you will form an alkene. You will regenerate the acid, otherwise it's not a catalyst, right? So when the acid catalyzed dehydration leads to more than one elimination product, because in this case we're forming one, but it is possible that you could form more than one. So again, regiochemistry, right? Same thing applies as when we were doing substitution elimination reactions. The more substituted alkene will be the major product. So for example, I could take something like this. I can protonate this. So sometimes you'll see H2SO4, sometimes you'll see just H plus. Just realize that this is your acid catalyst. We could either get our major product here, so the more highly substituted alkene, or we could get the minor product, which would be the less substituted alkene. So you can deprotonate either of those beta carbons. After your water departs. So this would be major, and this would be minor. And by major and minor, we're talking something like, 85-15 or 80-20 in terms of a ratio, right? Sometimes 90-10, but like 80-20, something like that. You don't have to come up with those ratios. Just realize that's kind of like the level we're talking about in terms of major and minor. Let's see, what else can we do? Well, let's see. We could do an E2. So we could do a dehydration reaction on a primary alcohol, right? So let's take just some ethanol. And we'll allow this to react with an acid catalyst. And unlike in an E1 reaction, what's going to happen is all in one fell swoop, we're going to protonate our alcohol. And then we'll do a backside attack, right? Let me just actually draw this a little more suggestively. I'm going to grab that proton with the base. So water or the conjugate base of your acid. These elimination reactions, a little more helpful to draw the bonds in. So we're going to grab that hydrogen. These are going to come up, form a double bond here, and water gets kicked off. So we protonate the hydroxyl group to create a better leaving group. And then water or some base is going to come in. It's going to deprotonate the beta carbon. The electrons are going to collapse between the two carbons, form the double bond, and kick off the leaving group. And you end up with your alkene plus water. And your acid catalyst comes back again. So for primary alcohols, we have E2 and we have SN2. For secondary and tertiary alcohols, we have E1 and SN1 mechanistic pathways. Might also behoove us to talk, since we did regiochemistry, we might want to talk a little bit about, and let me just highlight that for you. We might want to also talk about the stereochemistry. We talked about regiochemistry. What about stereochemistry? That is cis-trans or EZ, right? So the products that we get from the E1 dehydration of an alcohol are going to be identical to the products that you get from an E1 reaction of an alkyl halide. So this isn't something new that you have to sort of memorize or anything. It's basically when you're doing an elimination reaction, right? A unimolecular elimination reaction on either an alcohol or an alkyl halide, you're going to get both the E and the Z stereoisomers as products. But the major product is going to be the stereoisomer, in which the bigger group on each of the sp2 hybridized carbons are going to be on opposite sides of the double bond. So the one that, essentially the one that looks trans, right, where the little zigzag, right, because that stereoisomer is going to be more stable. That is, it's going to be lower in energy. It will be formed more rapidly. So a little example of this, and this is something we've already covered with the alkyl halides, but it doesn't hurt to give another example. We'll take this alcohol, and we'll hit this with acid, usually sulfuric acid. So we have a secondary alcohol here, which means we're going to be doing an E1, right? So what we're going to get, we can draw just the intermediate here. plus water. And then we're going to deprotonate one of the beta carbons. And what you're going to get is two stereoisomers. So you'll get this one, and then you'll get one where you've got both methyl groups on the same side of the double bond. And then, of course, so I'm taking the major regioisomer, right? There's also going to be the chance that you deprotonate that terminal like methyl group there and form a terminal alkene. But since that's going to be the minor regioisomer, I'm going with the major ones. This right here, using the major regioisomer, this will be your major stereoisomer. And this is trans. Both carbons, both sp2 hybridized carbons have a methyl group and then a hydrogen, right? So we don't have two alkyl groups on one of the carbons, right? So we don't have essentially three totally different alkyl groups or three R groups on the alkene. So we're not dealing with EZ stereoisomerization here where it's fine to use cis trans. This will be minor. This puts both of the larger groups on the same side of the double bond. It will be the minor product. So again, I'm just going with, I can see in this molecule, I've drawn an asymmetric alcohol, right? So you can create also this product. Right, if we were to deprotonate the last carbon. But that's your minor regioisomer. So I was sort of outlining the stereochemistry using the major regioisomer. So you can do all of the same reactions with alcohols that you can do with alkyl halides. You just have to set it up for success, right? So you have to create a better leaving group out of that hydroxyl group because OH minus, right, hydroxide is too strong of a base. So if we protonate it first and create a weaker base to leave, as in water, then we can actually perform these substitution elimination reactions just like we can with the alkyl halides. There's another type before I get going with a different reaction. I want to sort of like jump into the difference between just a regular garden variety alcohol and phenol. So we talked briefly about phenol in the aromatic chapter. So let me just mention its physical properties a little bit here. So phenol versus cyclohexanol. So when we first started talking about reactions we can do with alcohols, we discussed the ease with which the leaving group would take off. And we talked about how OH minus is too strong of a base. Let's talk about the acidity of each of these compounds. So we have cyclohexanol versus, well, I wrote that and then drew them backwards. I'll do this for you so that it's not matches up with the title there. So we have phenol versus cyclohexanol. One of these, so they both look like regular old alcohols, right? But one of them is attached, the hydroxyl group is attached to an aromatic group. And in the aromatic section, we talked about how that is a weakly electron withdrawing group. So meaning if I were to use one of these molecules as an acid Or if I wanted to use one of these molecules as a nucleophile, what if I wanted to use the lone pair of electrons on the oxygen to attack some other molecule, right? If I want to use an alcohol as a nucleophile, we saw in the substitution elimination chapter that we could use alcohols as weak nucleophiles in SN1 processes and E1 processes, right? No problem. But you're not going to be using phenol, right? It's a different kind of alcohol. And the easiest way to envision that is to deprotonate it. If I were to deprotonate this, I end up with a species that, due to resonance, is more stable than if I were to deprotonate the species. I can delocalize those lone pairs of electrons into the ring and by resonance this anion is more stable. So what that means is it's less reactive. So phenol creating a more stable conjugate base, phenol is more acidic than cyclohexanol. So in other words, the pKa is going to be lower for phenol than it will be for cyclohexanol. So if you're going to be, and what does that mean for us? It means that phenol will make a poor nucleophile. The electrons aren't necessarily as available to attack an electrophilic site on another molecule. It's more acidic than cyclohexanol, right? So cyclohexanol can be used as a nucleophile. It can be used as a weak nucleophile, but not as weak as phenol. In other words, the lone pairs of electrons are more localized on the oxygen. In cyclohexanol. So the lone pairs of electrons on phenol can be delocalized by resonance into the ring, right? So we can draw little resonance structures where we can convince ourselves that those electrons aren't nearly as available to attack an electrophile on phenol as they will be for cyclohexanol. And consequently, the acidity of phenol is greater than that of cyclohexanol. So that's an important distinction to remember. We go by their pKa. So in other words, this right here will have a lower pKa than cyclohexanol. Another type of reaction that we see with alcohols are oxidation reactions. You can actually get other functional groups by oxidizing an alcohol. We're going to try to keep this as simple as possible and just talk about a couple of reagents, a couple of characteristic reagents that we should be mindful of. We've noticed sort of in Gen Chem anyways, that, or even in the alkene-alkyne chapter, that when we see a reduction reaction, we see an increase in the number of carbon-hydrogen bonds, right, in the product. So I could take an alkene and I can hydrogenate it and turn it into an alkane, right? So I see an increase in the number of carbon-hydrogen bonds and a reduction. The oxidation process is the reverse of a reduction. So therefore, the oxidation reaction will decrease the number of carbon-hydrogen bonds. Or in organic chemistry, we say we're noticing an increase in the number of carbon-oxygen bonds. And so there's a whole pile of different reagents that you can use to oxidize alcohols, right? But we're going to focus on two. So with primary alcohols, so say for example, ethanol, we can oxidize this molecule, and I'll go stepwise here, with chromic acid. In other words, and this can be presented a number of different ways. You could see it written as Jones reagent, or just Jones, right? In water. And what you're going to get after the first oxidation, and you're changing the oxidation state of the carbon that bears the hydroxyl group, decreasing the number of carbon-hydrogen bonds, increasing the number of carbon-oxygen bonds. The first oxidation state up from the primary alcohol will be the aldehyde, and it won't stop at the aldehyde if water is present. So we have Jones reagent, which is chromic acid, meaning aqueous conditions. The aqueous conditions is sort of the key feature here. This will be oxidized straight up to the carboxylic acid, which is the next oxidation state for that carbon. So here we have our primary alcohol. Here we have an aldehyde. And here we have a carboxylic acid. So if you are going to be subjecting a primary alcohol to oxidative conditions and you use Jones reagent, right, a strong oxidizing agent in the presence of water, your alcohol will not stop at the aldehyde. You will go all the way up to the carboxylic acid. What if you wanted the aldehyde? There is a way, there's a method, there are a number of ways actually, but the one that we're going to focus on is we're going to oxidize the primary alcohol using a different oxidizing agent called pyridinium chlorochromate. This is done under anhydrous conditions, usually in methylene chloride. So by convention, I should mention this to you, if you see a molecule underneath the arrow and it's not taking part in the reaction, it's usually because that's where, by convention, we stick the solvent. Sometimes the solvent is one of the reactants. In this particular case, it's not. This right here does not contain water. It's an anhydrous solvent. And I, in the actual lecture notes, gone through and shown proposed mechanistic pathways for these. You're not going to be responsible for those. I just want to I wanted to highlight those in the notes so you could see why the water is important, why it goes up to the carboxylic acid. So with PCC, that is pyridinium chlorochromate, in methylene chloride, sometimes this is written as DCM. So this is the solvent. So sometimes methylene chloride, otherwise known as dichloromethane, you might see DCM. because there's a lack of water in the reaction pot, this will stop at the aldehyde. So if you want the aldehyde from a primary alcohol, because you won't be getting an aldehyde from a secondary alcohol, you have to choose your reaction conditions wisely. So primary alcohols with Jones reagent, or that is chromic acid under aqueous conditions, will give you the carboxylic acid. So this right here is going to be what you end up with if you take a primary alcohol and subject it to Jones reagent under aqueous conditions. If you choose to oxidize the primary alcohol and you wish to get the aldehyde, pyridinium chlorochromate is the reagent that you want to use. And that is done under anhydrous conditions. If we take a secondary alcohol, and we oxidize it, and any oxidizing agent will do, but Jones is pretty effective. It's gnarly, but it's pretty effective. We could take, say, for example, cyclohexanol. Jones reagent under aqueous conditions. You will end up with a ketone. You can't get a carboxylic acid, and you're not going to get an aldehyde because you have a secondary alcohol. You will get a ketone. So the oxidation of a secondary alcohol will give you a ketone. In all of these cases, and I'll draw this in a different color, the hydrogen that's attached to the carbon whose oxidation state will change is required in the mechanism. So a tertiary alcohol where that hydrogen doesn't exist, tertiary alcohols do not undergo oxidation. Because notice how there's no hydrogen attached to that carbon. So if you see this symbol, that means somebody is generically telling you they want to oxidize something. No reaction. Because you are missing that hydrogen. And it is required in the mechanism, we believe. But according to data, tertiary alcohols do not undergo oxidation reactions. So those are sort of like the token reactions that we see with alcohols. We can dehydrate them, right, and form alkenes. We can do substitution reactions with them if we convert the hydroxyl group to a better leaving group. We can oxidize them to get other functionality. We can get a carboxylic acid, an aldehyde coming out of a primary alcohol, or we could get a ketone coming out of a secondary alcohol. Tertiary alcohols are pretty much good for substitution elimination reactions. You're not going to oxidize a tertiary alcohol because it's missing the hydrogen on the tertiary carbon. So that's really kind of where it's at in terms of the chemistry that we can do with alcohols. One thing I would like to just briefly add on to this video is thiols. So we really only need to focus a little bit on their physical properties and their nomenclature, but thiols undergo pretty much all the same reactions as alcohols. They're simply just sulfur analogs, right? So they used to be called mercaptans. So you may have heard of mercapto something or other, right? If whatever, whatever name, mercapto ethanol or something like that. Because uh, the sulfur or the thiol itself forms a really strong complex with heavy metal cations, like arsenic or mercury. That is, the name mercaptan came from the fact that they capture mercury. So, for example, um, used to be called mercaptans because they'll form a complex, a strong complex. So there's your thiol, right? With mercury salts. So if you take, say, the mercuric ion, what you get out of this is here's your thiol, or a thiol, I should say, the sulfur analog of an alcohol. Here's your mercuric ion. And this is your thiol mercury complex. So they're said to capture mercury, so they were called mercaptans, right? So, in terms of, there's just a little bit of history for you, because we do use the word mercapto sometimes in the nomenclature. So, just so you're aware of where it comes from, thiols are usually just named by adding the suffix thiol to the name of the parent hydrocarbon. So, it's pretty easy, right? If there's a second functional group in the molecule, then you identify it by its suffix and the sulfhydryl group. So, that sulfhydryl group is that SH instead of hydroxyl, we have a sulfhydryl, um, can be indicated by its substituent name, mercapto. So then, if you have a functional group on the molecule that takes priority, then we're going to name that sulfhydryl group as a mercapto group. So, like other substituents, we're going to place that name, that substituent name mercapto, before the name of the parent hydrocarbon. So easier to see examples. Let's just start out with, well, we could start out with the thiol we just used. So what you're going to do is you're going to add the suffix thiol to the name of the parent hydrocarbon. The parent hydrocarbon here would have been ethane. So we have ethane, thiol, all one word. Or I could draw something a little bit more complicated and put a substituent on the molecule. So there you have your sulfhydryl group, right? And again, just like you would with an alcohol, you're going to prioritize your functional group. So we're going to number this to give top priority to the sulfhydryl group. So 1, 2, 3, 4. So on carbon 3, we have a methyl group, 3-methyl. -1 butane thiol. So you're probably sitting there going, well, when do you use the word mercapto? So in that kind of a situation, you're dealing with a sulfhydryl group as a substituent. So in other words, some other functionality on the molecule is going to take priority. This is kind of the first time we've had this situation happen to us where we have two different potential functional groups. One of them is going to take priority over the other. So for example, we could have our sulfhydryl group, and then just to keep it simple, we'll put like an alcohol. And in this case, since we are prioritizing the alcohol, that gets carbon 1, that gets carbon 2. Oops. And in that case, the sulfhydryl group becomes a substituent. If that happens, we use the word mercapto. So in other words, this will be 2 dash mercapto ethanol. So their nomenclature isn't too complicated. And in terms of prioritizing functional groups, this is sort of like the first time we've run into what takes priority if you have two functional groups on a molecule. So if you've got pretty much anything with an oxygen is going to take it to have a higher oxidation state for the carbon. So we're going to end up with priority. So it's kind of a general rule for how we prioritize our functional groups if you've got one molecule with a bunch of different pieces of functionality on it. So whatever one is more oxidizable or more oxidized will take priority. So your alcohol will take priority over the thiol. In this case, we'll name the molecule for the alcohol. And in terms of their physical properties, you can lean back on some of your Gen Chem stuff. So physical properties, like intermolecular forces of attraction, so hydrogen bonding, all that kind of stuff, acidity, basicity, whatever. Boiling points, etc., right? So sulfur, the things that we might want to keep track of, sulfur is less electronegative than oxygen. The other thing we want to keep track of, or at least point out, is that sulfur is larger than oxygen. Why am I comparing sulfur to oxygen? Because they're in the same group. So if you look on the periodic table, sulfur is right underneath oxygen, right? It's the next energy level down, the next period. Third period, you find sulfur. It's larger, so it has a larger atomic radius. It's less electronegative than oxygen. So the electronegativity of sulfur rivals that of carbon, right? Just something to keep in mind. And because sulfur is not as electronegative as oxygen, thiols are not as good at hydrogen bonding. So thiols aren't as good at hydrogen bonding than alcohols. So if they're not as good at hydrogen bonding as alcohols, what suffers? Well, all the physical properties associated with intermolecular forces of attraction, right? So in other words, the boiling points, if you're comparing molecules with similar masses, the boiling points are going to be lower than that of an alcohol, right? So ethane thiol will have a lower boiling point than ethanol, for example, right? So ethanol has a boiling point of 78 degrees Celsius, and ethane thiol is somewhere around body temperature, which is like 37 degrees Celsius. So sulfur atoms are bigger than oxygen atoms. So what does that mean? It means that if we were to deprotonate a thiol, So we're going to take the hydrogen off of a thiol like you would if you were deprotonating an alcohol. That negative charge on the thiolate ion is going to be spread out over a larger volume of space than the negative charge on an alkoxide ion. So if I deprotonated, for example, methane thiol, what I get is this. And if I deprotonate methanol, I get the methoxide ion. When we use words like alkoxide, we're saying the alkyl group that is attached to the oxygen that has been deprotonated is referred to as an alkoxide. If you want to be specific and you know what the alkyl group is, you can name it, right? So methoxide, right, would be the alkoxide we're talking about here. So since sulfur atoms are going to be bigger, since they are larger, their atomic radius is larger than oxygen atoms, when you deprotonate a thiol, the negative charge is spread out over a larger area. What does that mean? It means that it's more stable. So therefore, thiols are going to be stronger acids. Let me say that again. This will be more stable. This will be less stable. And if the thiolate ion is more stable than, in this particular case, the methoxide ion, then it means that this was more acidic or easier to deprotonate. You made a more stable compound. This will have a lower pKa. This would have a higher pKa. If this is more stable, it means that it's less basic. And this is more basic. That negative charge on the methoxide ion is more localized on the oxygen, right? It's spread out over a smaller volume of space. And so another thing to note, though, a little odd, is that even though the thiolate ion is going to be a weaker base than the, in this case, methoxide ion, the larger thiolate ion is going to be less well solvated. And so it ends up being a better nucleophile. So even though it's less basic, it's a better, but it is less solvated. Remember, worse hydrogen bonding. And so therefore, it ends up being a better nucleophile. So your thiolate anion is going to be more nucleophilic. It will be less basic. So it seems like that's, contrary to what we've been saying, because more basic is better nucleophile. But in this case, we have to talk about the difference between the size, right, of the sulfur. It's also less electronegative. So also larger and hanging on to those lone pairs of electrons just a little bit less fiercely than the oxygen would be. So better nucleophile, weaker base right after it's been deprotonated, meaning the protonated version, the thiol, is going to be more acidic than its oxygen analog. Physical properties there. Um, Leaning back a little bit on our Gen Chem stuff. So all of the chemistry that you can do with an alcohol, you can do with a thiol, but bearing in mind, right, these differences in physical properties due to the electronegativity and the atomic radius or ionic radius. So that's about where it's at for alcohols and thiols. Um, in the next video, a separate video, I'm going to tackle ethers and a special kind of ether, a cyclic ether, a three-membered ring, right, containing an oxygen called an epoxide.